Hello, everybody. My name's Corey, and we're going to be discussing this next section is on thermodynamics. It's kind of a two-parter. We're going to be discussing the AFLOW Convex Home module, and then the AFLOW-CCE module, which was created by Dr. Rico Friedrich. All right, so let's go ahead and get started. Okay, so the major question that we're looking to answer for this session is whether a material will form. Okay, so that's the goal of this lecture. We can talk about it from a very broad perspective. There's two major controls of or phenomena that are dictating whether a material will form. And they work together. You have to consider both of them, kinetic and thermodynamic. So what is kinetic here? Okay, so we have here a plot here of a reaction. So we have some reactants. They're going to undergo some transition state. There's going to be some reaction, and then we're going to get a final product. Okay, and so if we're under kinetic control, the system has some finite temperature given, let's say, by the temperature of the system. And being that if you look at reaction pathway 1 to product 1, this green one here, the reaction pathway has a smaller energy than the energy of the system. And therefore, the reaction could complete fully and successfully. And so we expect that if the system's under kinetic control, that the reactants will form product 1. Okay. However, if we look exclusively at the thermodynamic control, we sort of ignore what's going on in the middle here. And we just look at the energy differences between the reactants and the products. And so you can see here that while before we formed product 1, product 2 technically has lower energy. And so if we're under thermodynamic control, the reactants are gonna realize they're gonna form product 2. Okay, so that's the difference here. We need to consider both in general for understanding whether a material will form, but as an approximation, we're going to look just at thermodynamic control, and we're going to see what information we can extract in this regime. Okay, so thermodynamic stability. We want to understand whether a mixture or an alloy system here, this example, we have palladium and platinum. We want to understand whether this system is stable to decomposition. One pathway of decomposition is it could decompose into its pure components. So that's pure palladium and pure platinum. It's the same idea as if we try to mix oil and vinegar together. We want to know whether they're going to phase separate, which they will eventually, or if they're going to form a nice homogeneous single phase system. This is dictated by the Gibbs free energy, which we calculated in the previous lecture with Dr. Tower. So the Gibbs free energy dictated by temperature, pressure, and stoichiometry. These are kind of the variables that we work with when we're doing experiments. We can vary the temperature and pressure. So this is the thermodynamic potential of interest. And there's two major terms. There's the enthalpy term, and then there's a term, the entropy term, which is scaled by the temperature. And so in order for us to be in thermodynamic stability, we want to realize the minimum energy configuration. So that means that we're going to minimize the Gibbs free energy. And a corollary to that is that we want to maximize the entropy. So when we simultaneously lower the Gibbs free energy, we maximize the entropy, that's going to be stability of our system. This is the second law of thermodynamics. We're going to ignore entropy for this discussion. If you join me tomorrow, I think it's the last session, we're going to discuss how we can introduce or approximate this term here. But for right now, we're just going to focus on the enthalpy of the system. How do we calculate the enthalpy of the system? Well, enthalpy is the internal energy plus, minus negative pressure volume term here. We're going to ignore pressure volume just for the sake of simplicity. And so we're just going to look at the internal energy of the crystal. There's a few terms here that, well, we can look at it from a sort of Taylor expansion perspective. So we can look at the individual energies of all the atoms. Okay, so we have a certain number of palladium and a certain number of platinum. Each of them contributes a particular energy to the system. We can look at two body interactions. And you can see here that there's that two body interaction, that energy from that interaction is going to depend on the distance between those two components, and of course which two components are bonding or interacting. We can look at three body interactions, where we can look at where now we start to introduce phenomena that are dependent on the angle. And so you can see some of these interactions that are happening here, non-bonding interactions that are happening between these three bodies, and so on and so forth. For the perspective of this talk, we're going to be looking at we want to understand. So we're going to be calculating enthalpy using density functional theory. That's actually what we were doing in the first talk when we're doing the calculating the energies with VASP. And so the energy that we get for the system from density functional theory, as we calculate it when we relax the system, we get the energy. This is going to be the internal energy, or the enthalpy, at zero pressure and zero temperature. Okay. So you already know how to get the enthalpy from calculation. So we can calculate the enthalpies of our alloy system here, of our mixture. We can calculate the enthalpies of our pure phases here. And we're interested in calculating the enthalpy of the overall reaction. So we're going to calculate what's called the enthalpy of formation. So we're going to zero out the enthalpy of the pure phases, and we're going to subtract that off from the enthalpy of the alloy mixture. And that's going to give us the enthalpy of formation for our alloy. Okay, so basically we take the initial enthalpy that we calculate from VASP, from DFT, and we're going to subtract off the stoichiometric weighted enthalpies of the pure phases. That gives us the enthalpy of formation. Okay. Okay, so now we're going to look at, so I told you that our goal is to understand whether the Gibbs free energy is minimized in this reaction. A useful way of you can go in and you can do the calculation, using the numbers here, but a nice way of doing this is actually by visualizing the thermodynamics that's going on. So here we have a plot of the formation enthalpies versus the composition. Okay, so we have our pure components at the top. Remember, we zeroed out their formation enthalpies. And then we have our alloy mixture. We have a 50-50 mixture. So it sits here, and we have some, in this case, it's negative. And that's important because we know that the system is stable with respect to decomposition to its pure phases. So the fact that it's negative with respect to the tie line of the pure phases, this is how we visualize it. The visualizing the difference between the two enthalpies. This tells us that we are stable with respect to that decomposition. Okay, so if this were positive, then you would expect the system to decompose. Now, the situation gets a little more complicated in that if we want to understand stability of the palladium platinum system as a whole, we need to look at phases that span the full compositional range and that have different arrangements of atoms. So if you think back to David's lecture, to Dr. Hicks's lectures on different prototypes, you could have a 50-50 mixture, but have different arrangements of atoms, different prototypes. So we need to explore at least those two degrees of freedom, the composition and the way we arrange the atoms. And so you can see here that I've just visually showing a few examples of different. So here we have different arrangements of atoms, even though we still have a 50-50 mixture. And then we have different compositions, different amounts of palladium versus platinum, different ratio of white to blue atoms here. And in order to understand the sort of the global stability of the system, we need to look at all the possible decompositions and see which phases are going to be stable to all the possible tie lines that we can create. Okay. And what we're going to build is called the convex hull. Okay. So mathematically speaking, this is the the convex polytope, or the shape that's going to touch all of the outer points. You can think of this as wrapping a giant rubber band around our data points here and seeing where the rubber band touches. What points does it touch? Those are the outmost points. Okay, so you can see here that I've highlighted the points that are on the convex hull. These points are stable to all possible decompositions on this plot. Okay, we have about 527 different entries that are included in this calculation from AFLOW. Okay, so we have 2 points here, these two phases, and they're connected by a tie line of the convex hull. And what this tells us is that these two phases, this is a two-phase equilibrium. So these phases happily coexist together. If we take a mixture of these two phases, they're not going to want to mix. They're just going to stay separated, and they happily coexist, phase separated together. Okay. However, points that are not on the hull, so for the rest of the points that don't define the convex hull, these phases are unstable with respect to decomposition. So we have PD2, PT3 here. And if we want to understand what it's going to decompose into, visually, what we do is we take our point, we drop our eyes, take a vertical line straight down to the convex hull, and we look at the facet that it touches. The 2 points that define that facet are going to be the 2 phases that it's going to decompose into. So you can see PD2, PT3 is going to decompose into 50-50 mixture of PD, PT, and then PD, PT3. Okay, and we can balance that equation just by, doing we can analyze we can balance it chemically. And so we get that reaction here. The distance, so the distance that it had to, in terms of energy, that distance between the point that we're looking at and that vertical distance down to the facet, that actually quantifies the amount that the reaction's being forced into that direction. So this is the distance to the hull, and that tells us what is the driving force for decomposing our pure phase, or excuse me, our mixture into its decomposition products here. So if this distance is very large, the system has a very high tendency to want to decompose it's going to do it. You can think of it as wanting to do it very quickly. There's going to be a high tendency to want to do that. The distance is very small. You can imagine that it's going to take a while for that reaction to happen. Now, keep in mind that these calculations are performed at 0 temperature and 0 pressure. And so if we're using this as a proxy for understanding how alloys are going to decompose, let's say at room temperature, we're going to want to, we understand that that if we perform our calculations at room temperature, incorporating vibrational contributions, all of these contributions that occur at room temperature, then our picture is going to change a little bit. Okay. And so a useful measure of whether we are going to, how much of this picture is going to change as we incorporate temperature effects, we can look at room temperature excitations and use that as sort of a threshold for whether we expect the system to really decompose, or it's possible that that system could be stable, or at least metastable. So the fact that we have such a small distance here tells us that even though PD2, PT3 is off the hull, it's possible that it could still be stable or metastable at room temperature, because it's less than 25 MeV, which is the amount of energy at room temperature, these room temperature excitations. Okay, a little bit about the algorithm so AFLOW performs this algorithm, this convex hull analysis. It does it automatically. There's some useful or important. Oh, I got a question here. Would PD3 PT? Let me go back to the other slide. PD3 PT and PT3 coexist together or react with? No, let me see. Yes, these two phases coexist. They're not going to, they're going to stay separated. So they happily coexist. Are they? Wait, I'm confused. I don't quite understand. PD3, PT2. So this phase here is going to decompose into these two phases. So this phase will no longer exist once that reaction is completed. Okay, I hope that answers your question. For a given vertical cross section in the convex hull plot, how were different arrangements generated? And is that list exhaustive? It's a very good question. You're alluding to the fact that we, you can imagine that. So we're creating this prototype encyclopedia based on experiment, what based on the literature and what experiments have found to be some prototypes that exist in nature. But we're continually finding more prototypes. And so we can imagine that we could perform more and more calculations based on different prototypes. How do we know that we've converged this picture? I think that's really the heart of your question here. You don't know. So what we do is we have a heuristic based on binary. So we've done an analysis of the binary convex hulls, so mixtures of two components. And we've looked at at what point do we start to see the phases that we expect to see in experiment. And at least for the intermetallics, what we see is that if we have at least 200 entries, that the convex hull is sufficiently converged for two components. So this is a heuristic that we implemented in AFLOW automatically, and you can actually change that if you decide that you want that heuristic to be higher or lower. Okay, so I hope that answers your question. But really, we don't know if this is really, there might exist a phase that we haven't calculated that would really change the landscape here, might become a stable point. There's a descriptor I'll talk about a little later, which will consider some of this, will consider part of this question. We'll try to answer a bit of this question. So we'll discuss that in a bit. Okay, so we'll keep going with the slide. So okay, so since this analysis is performed automatically and in a high throughput sense, it's possible that there exist outliers in the data. Okay, so if you look, the majority of the points exist up here, and this one calculation has a very low energy. Okay, so it's possible that, for instance, this calculation had some different input parameters. Okay, maybe we relaxed it a little differently. It's possible that it didn't converge. And in which case we're seeing, basically there's a lot of reasons that we might have an outlier here, and AFLOW will do its best to remove that outlier. Okay, so there's an automatic outlier that's in detection removal system in the convex hull, and there are also parameters or flags that you can give it to not do this analysis. So perhaps it's possible that this is truly the minimum and that the other points are not. And so you can actually turn on and off this outlier detection removal. But since we do these things in a high throughput sense, this algorithm for outlier detection is included automatically. We discussed, we might have shown you from some of the, when we looked at some of the results on the website, you saw that we have duplicates because we pulled data from the ICSD database, and the ICSD has more than one entry, or it has more than one entry for particular compounds that are all equivalent. Maybe they were done at slightly different temperatures, different pressures. So it's possible that there are duplicates in our data. AFLOW-CHULL will actually go in and analyze for the points that are on the hull. It'll actually figure out which points are equivalent, and determine the one that is the minimum energy, and pull that value out for you. So all of these might be duplicate entries, and the convex hull analysis will actually tell you these are duplicates, they're not unique entries. This is important when you're doing this distance to the hull calculation, because if they're equivalent, you're not going to want to take the distance to be basically the error in the calculation. You might imagine that there's going to be slight differences in the energy among these compounds. Since they're equivalent structurally, their distance to the hull should be 0. Okay, let's say. So for right now, we're going to actually play online with the convex hull module. So I'm going to close out of here, and I'm going to share my screen. And I'm going to ask that we all navigate together to aflow.org. I'll just do it. Go to aflow.org. Okay. And we're going to scroll down and we're going to go to the Convex Home module. I'm going to click there. Okay. And we're going to look at a whole together. We're going to look at AGAUCD. Okay, so you're going to want to type that in. Let me put my slides up next to mine. I'm going to put this here. I'm going to make this smaller. Okay, so AGAUCD, and we're going to hit submit. Okay, and in a few seconds, you should get a Hall visualization. Okay, so we've been looking at 2D halls, and now it's important to realize that we can actually look at 3D halls. Okay, so the 3D hall is going to add another compositional dimension, and so what we, instead of having a plot where we had, let's go back here, where we had the two components along the x-axis and then the formation energy along the y. Now that we're going to have three components, so we're looking at a mixture of, well, in this case here we have a mixture of silver, gold, and cadmium. So we have the compositional space is going to be the xy plane here, and then the z direction is going to be the formation enthalpies. Okay, and before we had tie lines that made up the convex hull. Now we're going to have tie surfaces, and it's going to be highlighted here in color. So you can move around, you can zoom in and out with your mouse, and you can actually take a look at the convex hull polytope. So now it's a set of surfaces. So I'm going to highlight the hull points so you see how it's created. Okay, so these points here define these triangles. These triangles are going to be, if you take the sum of all the triangles, the union of all the triangles, that's going to define that convex hull there. Okay, so this is the minimum energy surface that defines, basically this surface is a visualization of the minimum Gibbs free energy. Okay, so what do we have here? We have, we can pan around, we can zoom in. Okay, so I'm gonna not highlight the hull points. What's nice about this visualization is that if I click on an off hull point, it'll actually show me the decomposition. Okay, so you can see, you just take your pointer, it's going to drop right down to that. Now, instead of having tie lines, we have surfaces. So we have 3 points that it's going to decompose into. So if the reaction goes successfully and completely, this compound is going to decompose and it's going to form these 3 compounds. Okay. And so what's nice to look at is that, so that one, it's going to decompose into 3. Ooh, reset. It's going to decompose into 3, but there are some that sit right on top of one of the edges of a facet. So it's not going to decompose into 3 components. It'll decompose into 2. So this is an example of one of those there. Okay, so you have, as you go into higher dimensions, you can have decompositions of 2 components, of 3 components, and so on and so forth. So you can see that the number of decompositions, it's the number of pathways is going to increase, and you get a sense of that from this visualization here. Okay, so here you have one of the things I want to show you. If you highlight all the hull points and you click on one of these hull points, it's going to take you to a new page. You're going to give it a few seconds. And you're going to see that there's going to be some cards that get populated. Okay. So what do we have here? So for every hull point, we have a card, and it tells you the AUID, that it's ground state, gives you the prototypes, the space group, the energy. Here we don't have any. It's on the hull, so there's no. Well, it's not gonna have any formation enthalpy. Distance to the hull, and some of these other. I'll be talking about what these are in a few slides. But the most important thing about this slide here, this card, is that if you click more info, it'll open up the entry page with the full set of calculations for that compound. Okay, so now you can go in, you can play with the structure and look at all the other properties. Okay, so everything is very well connected inside of this universe of data inside of AFLOW. Okay, so now if we click back to the selected hull. All right, so what I would like you to do, so you see here that we have 3 buttons here. We have download PDF, download text file, and download the JSON. The JSON is very nice for the Python interface. Text file is visually nice if you like to look things in VI or in the text editor. We're going to click on download PDF. And you should get a PDF that you can open up. Okay, I'll give you a few seconds to do that. And if you're able to get that PDF successfully, you're going to see that we have the first page of the PDF is a nice visualization, or it's going to be a projection of that full convex hull space that we had here, right? So reset. So if we're looking at the picture from the top, this is what we see here. Okay, and the colors will give you a sense of depth. Okay, so you can see here that it's deeper on this edge here, which is exactly what we see here, right? So there's kind of a dip here, and that's what that color is showing you here. All right, and this is that picture here there, and then the rest of the document is basically a report of all the compounds that were used to make the convex hull, and they're organized by their stoichiometry. Okay, so all the compounds that have this reduced formula are sitting here. Let me make it a bit bigger so you can see. There's a lot of data, so the text is a little small. Okay, this side. Okay, so what do we have here? So these are all individual calculations from the AFLOW database, each one of these. If I click on one of these, it's going to open up the entry page for that calculation. Okay. So what are we showing here? So this composition here is unstable. Okay, so this entry exists above the hull. For points that are unstable, you're going to see that they're labeled as unstable. We get the AUID, the original space group, and then the relaxed one. Sometimes they change in the calculation. We get the spin per atom, the enthalpy of formation. This term here is the entropic temperature. I'm not going to go into detail what the entropic temperature is, but basically it's the enthalpy of formation divided by the ideal entropy. It's a descriptor that was used in the past for analyzing materials and finding compounds that were interesting from an entropic perspective. So this is a temperature descriptor, and then this is the distance to the hull. Okay, so you can see that this has a very large distance, 162 MeV per atom. That's much larger than room temperature excitation. So this compound is definitely going to want to decompose. And then we give the decomposition reaction. Okay, so that's for unstable points. For stable points, you'll see that it says ground state. The points that are the point that defines the convex hull, that sits on the convex hull, is highlighted in green. And then we have some points that sit on top of it. The points that are highlighted in orange have the same relaxed space group. So you can think of them as being similarly structurally. So they might be interesting from that perspective. And then we give vertices of the facets. So this point here, AG2, AUCD, this is this point here. These vertices, what it's going to tell you are the different triangles that touch this point. So we'll give you the combination of this triangle. We'll give you the combination of this triangle, and so on and so forth. Okay, so that's what these vertices of the facets are. So we give the vertices that of the triangles that touch that point. We have two additional descriptors here. I'm going to discuss them in the next slides, but we have the stability criterion here. That's the delta SC. And then we have the N+1 energy, which is written here, 17 MeV. Okay, I'll discuss what those are in the upcoming slides. The last thing I want to mention about this report is that it's really interactive. So it's nice, you can print it out. Printing it out is fine. But if you work with it on the web, the thing I want to point out is that if you click on this point here, it's going to bring you to that respective part of the report. Okay, so this is 23 pages. If you click on these links, it'll take you to the web links for the entry page. And then if you click on these links, it'll bring you to that respective part of the document. So this is really a working document. If you work with it on the computer, you can really play around and go to different links and see what's going on with those relevant compounds. Okay. So this is what we're going to use for exercises primarily in the next slides. Okay, so we're going to continue on. If anyone has, I see there's a question, I think, or a comment. Is positive HF also proof of instability? Okay, so positive HF, remember how we define the formation enthalpy? It's with respect to the pure phases. So the fact that it's positive means that it's and remember, we'll keep in mind that energy is all relative here. So the fact that it's positive means that it's going to it's higher in energy than with respect to its pure phases. So it's going to decompose with respect to its pure phases. If it's negative, it might decompose into a binary. Okay, so let's look at this picture here. I'll make it. So if we had entries that had positive enthalpies, they're at the top here. I'm not even showing them because they're not worth showing because they're going to decompose into the pure phases. So if it's got a negative enthalpy formation, that the point is that having a negative formation enthalpy does not mean it's stable. So meaning if it's negative, that means it's stable with respect to the endpoints, but it may not be globally stable for the system. That's the idea. Does that make sense? I hope that answers the question. Okay, let's keep going. So we're doing okay on time. Okay, great. Okay, so now there's a few things I want to talk about. So you might ask, well, why is some of this data relevant? For instance, why are the vertices to the fastest? Why do I need to know that information? I just want to describe, I'm going to go through a few, I want to relate this data back to the material science. What have we used this data for in terms of finding new materials or understanding materials in a different way? So I'm going to go through very quickly through 3 or 4. This is the conclusions of some papers we've read in the past. So I'm just going to go through them very quickly, but feel free to ask questions. So if we want one of the types of materials that we've looked at in the past are called super alloys. Okay, so these materials have very nice mechanical properties at high temperatures. One of the ways that we can get materials that are very hard, in particular at high temperatures, is called age hardening. This is a procedure that can be done experimentally where we perform a temperature we perform a particular temperature prescription. And what happens is that, okay, so here we have a system that's aluminum and copper, and you can see that copper it's basically a dopant in the system. Okay, it's randomly substituted in this overall aluminum matrix. Aluminum's FCC, if you remember. If we perform a particular temperature prescription, then what happens is that it's there's going to be a precipitate that forms inside of this, what's called the host matrix. So this is the host matrix. Okay, so we still have aluminum and copper on the outside, but then we get a different phase that forms these little precipitates inside of the overall host matrix. Okay, so this compound here is different. It has a different phase than that of the host matrix. Okay, this is the precipitate. And these precipitates are going to make it very hard for atoms to slide past each other, and that's going to increase the hardness of the material. So that's what age hardening is. So how do we do it with the temperature? We take our material, we increase the temperature, and then we quench it. We decrease the temperature very quickly, and then we anneal it. So we increase the temperature a bit, not quite to the level that we had it earlier. And we allow for these precipitates to form. They form in this annealing process where we keep that temperature higher, that high temperature for a very long time period. Okay, and then we cool down to room temperature. So we were working with some superalloy compositions. Here's one example. And we knew in this particular study that the composition existed somewhere along this red tie line. Okay, in this ternary phase diagram. In particular, we might be looking at this composition, 0.7 and 0.3. Okay, so why is it important that we understand which phases are tied, or which phases are have facets that share they share edges with that particular compound? Because if we need the host matrix to be in two-phase equilibria with the precipitate, in order for the age hardening process to form, then we're going to want to have a tie line that at most, if it crosses this red line, it doesn't do so at this point. Because if we have a compound at this point, it could still be in two-phase equilibria with X, with the pure phase. However, if we have a tie line, like the green one here, that completely blocks off access to the host matrix, then we know that thermodynamically this combination of host matrix and precipitate, that's not thermodynamically stable. So that's one descriptor that we use to look at all these different combinations of A, X, B and look for which superalloys are going to be thermodynamically stable with the precipitate. Okay. Okay. The next descriptor I'm going to talk about is what am I doing on time? Okay, I'm okay on time. The next one we're gonna do is we're gonna talk about the stability criterion. Someone asked a very good question about how do we know that this diagram is really fully converged? Is it possible that there exists some phase that we've never explored before, we've never conceived of, that would change this diagram and form a new stable phase? Okay, well, this stability criterion, it's a way of capturing whether that's possible. You can think of it this way. It captures that, it tries to address that question in some sense. So we're going to look at phases that are on the convex hull. And I want to ask the question, how stable is this phase in particular, this green one here? So what I'm going to do is I'm going to remove the phase from the convex hull. Okay, so this is the line here is the full convex hull. I'm going to remove that compound, and then I'm going to recalculate the phase, the convex hull. You can see that new convex hull with these dotted lines here. And I'm going to ask how big is that distance from the pseudo convex, or from this fake convex hull, the pseudo hull. Okay, so that distance here. So if this number is very large, then you can say that this phase is going to be very stable. It's going to be hard, or you can imagine that you can associate this with sort of a probability of finding a new phase that's going to offset it from the convex hull. So if this is very large, then this point is very stable. We can imagine that as we continue to populate the convex hull, we expect that the points are not going to, it's going to require a very big difference in energy for it to offset that convex hull, to change the landscape there. So in this case, we have 6 MeV per atom, so it's not very large. So there's a study we did. Where we were looking for new magnetic systems, and we were looking at this Heusler prototype. Okay, so it's made up of 3 components. The Heustlers are very interesting because you can actually have non-magnetic components X, Y, and Z, and it could form a magnetic system when you combine them into the Heusler prototype. Okay, so we looked at a whole range of Heusler prototypes. We took this backbone structure. There's 3 of them. There's 3 variants of Heusler. There's the regular, the inverse, and then the half Heusler. And we took these 3 prototypes and we took combinations of 3, all the combinations of 3 elements from these 51 elements. Okay, so we made a lot of different candidates. Okay, so it's over 200,000 different structures. Of these structures, we looked at which ones were magnetic, which ones are ground state. One of the descriptors that we looked at to see whether it's going to be a really stable point is we looked at the stability criterion, and we asked the question, is the stability criterion bigger than 30 MeV, right? Remember, 25 is that magic number for room temperature excitations. We wanted to look at structures that were greater than, that had a stability criterion greater than 30. So that means that distance from the real convex hull to the pseudo one is going to be very large. And among the ones that had that distance that was larger, there were 2 that we picked out 4 in the study, and 2 of them formed magnetic phases. And I give you the results here for one of them. This is cobalt, manganese, titanium. This was a new magnet that we discovered from, we first predicted it, and then we synthesized it and realized that the properties we predicted were very close to that of the experimental results. Here we have the magnetization curve showing that it is indeed magnetic. It has a Curie temperature about 950 degrees, which we actually predicted in the study. And it actually forms the Heusler structure that we expected it would form. Okay, so this was a very nice finding. All right, the n+1 energy. This is the plot I showed you in one of the earlier slides. You see here that we have our pure components. We're not looking at palladium or platinum, just generic A and B. Okay, so for any components on the periodic table. This distance here I told you was the formation enthalpy, right? Because it's the energy difference of the alloy system from the pure components. Another way you can think of this is that it's the energy gained from going from one component to two. Okay, so there's a gain in energy that the system gets, or that there's a release of energy, because this energy the system's lower in energy. There's a release in energy from going from pure components, which have only A or only B, to going to two component system. Okay. You can also, so we've done this analysis for all of the binary mixtures all of the metallic components in the periodic system and periodic table. You can also do this for all ternary compositions. So we can look at all A, B, and C combinations. And we can look at the energy gained from systems that are stable. If there's an energy gain at all, it's going to be from going from the pure components or binary components to now the adding an additional species, adding a third component. So we can look at what is the energy gained from increasing the number of species in the system. Okay, and we can do this analysis for, we did it for all AB combinations, all ABC combinations. And here we have a plot of what the enthalpy gain is for all these different types of systems. Here it's a histogram. Okay, so in red are all the binaries that we have in AFLOW. In green are all the ternary systems, and in blue we have the quaternary systems. And so what do we see from this plot? Well, we see that with increasing dimensionality, there are going to be fewer compounds that show any gain. So you can see there's a lot of red, there's fewer green, and even fewer blue. So there are fewer compounds that show any gain, and the gain gets smaller as you increase dimensionality. Why is this? It's because fundamentally the competition to be on the hull increases with dimensionality. So for any compound to be on the hull for an AB combination, it really needs to compete with all of the other systems with having AB composition. Once we go to the ternary, you're now competing with the binary. So you're competing with all of the stable points in the binaries for all three of these, plus all of the other ternary compounds. So the competition to sit at the bottom to have the minimum energy continues to increase, because if you think about the 4 dimensions, now you're competing with binaries and ternaries and all quaternaries that exist on there. So the number of compounds that show any enthalpy gain is going to decrease as you increase dimensionality. This concept is going to be very important for my talk tomorrow. The last talk it's going to be important for disorder. Okay, so how are we doing on time? Okay, very good. All right, nice. So just want to show you some nice command line options. So I'm going to reduce my focus here. You should still see my screen, right? You should see my browser here and all that, right?
Yes.
Okay, great. So what we're going to do is, let's close this out. We're going to open up a terminal, module, load AFLOW. Okay. We're going to CD into day 2. We're going to go, sorry, one second, not day 2, day 3. CD into day 3. We're going to go into CHULL CCE. We're going to go into the 7th one, LS. Here we have a copy of the slides from today, so you can download them and see them. We're going to go inside of exercises. Okay. We're just gonna stay there. Okay, so okay, so there's a number of ways that you can interact with the Convex Home module. I've already shown you one. One of the ways you can interact with the module is on the website. So in the background, it's running these commands. It's going to run them on our server, and then it feeds you the visualization. It gives you the PDF, everything that I showed you from the website. What is it running in the background? Well, it's running these commands. So you can run AFLOW --CHULL --alloy. You can ask for the alloy system. Okay, you can feed it in the alloy system MNPD, and then you can ask it to print out different options. You can do a JSON, a text, or a PDF. By default, it's going to give you the PDF. There's a few other options. You can query the distance to the hull for a particular compound, a particular entry in the database. So you do -D2H, distance to the hull, and you give it the AUID. You can directly query a, it's a little bigger, 1 second. You can directly query a structure stability criterion, same way, --SC, and you give it the AUID. You can also query the energy of the hull at a particular stoichiometry. So why is that important? Because remember, we have, yeah, this is okay. We know what the energies are at all the facets, at all the edges, because that defines the edge. But what about in the middle? What about if we want the energy somewhere along the middle where we don't have a facet, but we're sitting, well, we have a facet, but we're not sitting at the edge. So we can actually query the energy of the hull at any particular stoichiometry. So since this is 2 dimensions, we only need to feed it in one coordinate because the other coordinate's implicit, right? If I give it 0.25, then that's going to be of MN. It's going to be MN 0.25, PD 0.75, right? So the other coordinate's implicit. So you just need to feed it in one coordinate, and that'll give you the energy at the other at that particular coordinate. Here are just some, just to show off. Here's some high throughput inputs that we use all the time. You can query multiple convex hulls, so you just feed it in a comma separated list, and it'll calculate them sequentially. This command is equivalent to this command here, where you can think of it as, so look. You have MNPT, PDPT. You have a common PT component to both of these. So the way you can do something like this, where you do MNPD, comma separated, colon PT, and that's going to do this combination, MNPT and PDPT. Okay, so this is a way of making a lot of different combinations. We can also do feed it in a list of all of the metals that we really focused on calculating all of the different prototypes and spanning the stoichiometry. lib2 is an alias for all of the different metals that we really focus on in the database. So you can run this, and it's going to make, if you do lib2, it's going to calculate, several, I think it's hundreds of thousands of convex hulls. And to get more information on the command line, you can do --readme = --CHULL. There's a Python wrapper. So I'll show you that here. I created a few directories for you to look at. Scratch is for you to play with if you want to go in and play with the command line. So you can go into that directory. There's nothing in it because you're going to basically run the commands, and then it'll print out the PDF. It'll do you can run it, get the JSON and whatnot. So here we have, if you go inside of Python, you'll see that there's some scripts. So we can run these in your own time, or you can run them in the breakout rooms. But the main script here is called AFLOW-CHULL. So I'm just going to show you this. You don't have to do this, but I'm just going to show you what's inside. But basically, this is a wrapper for the command line options. It's a nice Python wrapper for it. So you can run a few commands. So you can do get hull, which is going to return back basically the PDF of the hull. You can get distance to the hull, so you can actually feed in. Let me show you, for example. Hold on. I'm going to show you an example. So you can load in this separate Python module that I was just showing you, and I give you some commands. So you're going to feed it in the AFLOW executable. In this case, it's just AFLOW, or you can feed it in the path. You create this object, you define the alloy system, you can get the hull. So this is going to print out the PDF, and you can feed it in other options. Maybe you want to get the log of the output. So that's what I'm doing here. You can get the distance to the hull. You feed in the alloy system. You feed in the AUID, and you also feed it in other options if you want from that README file that I showed you. Get stability criterion, feed it in the AUID, and get the whole energy. This is a vector, right? In general, it's a vector. We're only feeding in one number, but in general, it's going to be 0.5. If you're doing a ternary, you're going to add another dimension, and so on and so forth, so that you can actually run this and run this example, and it'll start. You will see what's going on. It's actually going to pull the entries from the database, from our database, using our APIs, calculate the convex hull, print the results. So that's the Python module. You can also run the Jupyter notebook. So I'm going to run this very quickly. Okay, so if I come out of this directory, if I come outside of this directory and I go inside of Jupyter, I'm going to run this command that I'm showing you here. AFLOW --CHULL. One second. It's frozen. Okay. AFLOW --CHULL -alloy equals MNPD. And then I'm going to print equals Jupyter. And what it does is it creates a new directory. And what you can do is you could run Jupyter notebook Python notebook. Oops, one second. Oh, it's Jupyter. I think it's Jupyter. No, sorry. Your Jupyter directory is empty. Okay, we can address that in the inside of it's strange that it's empty, but we can address this in the breakout rooms. But in general, you should get the notebook, and then you could run this. You can change the alloy system here. You know, I fed in MNPD, but you can feed in whatever you want, and you can actually get a plot of the convex hull and interact with the convex hull through this Jupyter notebook. So so this is another way of interacting with our with our module here. Okay. All right, so we're gonna head out to the breakout rooms now, and we're gonna do some exercises. Let me make this smaller so I can show you what the exercises are. They're pretty simple. You're just basically gonna query different alloy systems and find data. What you can do, most of this you can do from the PDF. If you want to be a little more adventurous, you can do it with the command line. But what is the distance of aluminum cobalt, this aluminum 17 cobalt 12 from the hull? What is the stability criterion of TE2ZR? What is the energy of CUZR hull at 0.5? You can do this from online if you just eyeball it. You can do it that way, or you can run the command and get the exact value from the command line. And then what ternary compound has the highest stability criterion on the MNPD-PT hull? Okay, so we're gonna break up into our we're gonna break up into our breakout rooms. Resume. Thank you. We hit it at the same time. I just want to all right, we're going to let me share my screen. So first and foremost, we figured out what the issue is, I think, with the Jupyter notebook. So you have to go inside of the directory. Let me open up another. Okay, so this one is being occupied. Okay, this is okay. So when I ran that command, it created, no, this is a Python, sorry. When I ran that command, it created a directory called AFLOW-CHULL Jupyter. You have to go inside of that directory to see all the Python notebook stuff. Okay, so that's where it is. And once you open up the notebook and you hit run, you're gonna get a plot that looks like this. Okay, so you can click on any of these points, and it's gonna actually open up the the web page for it. So that's how you interact with it with the Jupyter notebook, and all the other commands I showed you through the Python, in that Python slide, they all work here as well. Get hull, get distance to the hull, that stuff. All right, so for the exercises, you should have been able to do all of them online. So I pulled up the hulls already. This is the ALCO hull. If you scroll down and try to find AL17CO12, you'll see that the distance to the hull is 243. On the TEZR hull, if you look for TE2ZR, you'll see that the stability criterion is 49. For the, oh, I guess I might have closed it. I did close it. Second, hull history, I should have it here. By the way, you can click on hull history and you can pull up all the hulls that you saw within this session. For the distance to the hull, you can actually just eyeball it. You can see that at 0.5, there's no point on the convex hull, but you can look and you can see that it's about 150, 160 MeV per atom is what the energy of the hull is at that point. You can also do it more rigorously. I actually ran the command earlier. So you can run it rigorously through the terminal. Let me zoom in a little bit. You can actually run AFLOW-CHULL minus ALLOY-CUZR energy hull equals 0.5. And that's how, that will actually give you the exact answer. And then finally, for the MMPD hull, PDPT hull, the ternary that had the highest stability criterion was this MN2 PDPT, which was actually the other magnetic system that we discovered in that study. You can see here that the stability criterion is greater than 30, so this would have been picked up by our analysis. Any questions? I see some stuff in the chat. Oh, perfect. Thank you very much for sending that. Okay, if there are no other questions, I'm actually going to move on to the second part of this talk. Okay, so we're going to cover a very important correction to these convex hulls and in general to the formation enthalpy concept, which arises because of problems in density functional theory. So our focus is going to be on what's called ionic materials, also called covalent materials. These are defined as materials that have a mixture of metals with non-metals. Okay, or low versus high electronegativity. So I highlight if you have something that has a blue and a green element or mixtures thereof, DFT is not going to do well with calculating the formation enthalpies. Ionic materials are very important from a technological perspective. There's these materials in batteries. They make up the screens, the silicon oxides, the screens of our tablets, of our phones, of our monitors that we're using right now. They're very important for high temperature applications, such as the ones that we might find in airplanes and in rocket ships and stuff like that. They're also very important for tools because these ionic materials will make up the coatings that go on the tools that make them wear resistance, that make them harder, things like that. Okay, so what is this issue I keep alluding to? So formation enthalpy, we defined this earlier as the energy of the system of the mixture minus all the sum of the pure components, right? If we have an alloy system where the two elements or the elemental reference phases have really different characters. So where one is a metal, right? So, if we have, let's say silicon oxide, the oxygen is going to be, what is the reference phase for oxygen? It's a molecule, okay? Whereas silicon is going to be a solid. And so what we're really comparing here is the fact that the compound phase is going to have these ionic compounds are going to have charge that is going to be isolated to particular regions of space. Whereas in metals, we really have this sea of electrons. Okay, so there's different characters of the two elemental phases and the compound. That's going to make it very difficult for DFT because DFT has intrinsic errors in how it calculates the energies. And there's sort of an error, there's sort of a cancellation of errors that that exists for metals that does not exist for ionic materials, where the two references are very different. So what I want you to think about here is that when we're designing new materials, we have this kind of pyramid of ideas that we want to have. So we want to be able to do these calculations in a high throughput sense. We want to be able to have something that we can run very quickly in a high throughput sense. We want to be able to do it ab initio using VASP, using DFT, and we want the calculations to be accurate. So for metals, we can satisfy all sides of this triangle with semi-local DFT using LDA, PBE, scan, etc. But for ionic materials, we have a missing edge. We cannot do calculations that are both high throughput and very accurate. The errors can be as large as several hundred MeV per atom in terms of calculating what the enthalpy formation is. This is what this module is looking to fix. It's this side of the triangle. It's the CCE calculation, okay? The other sides of the triangle can be satisfied with, for instance, high throughput and ab initio DFT. If we want something that's accurate and ab initio, but not necessarily high throughput, we can do a non-self-consistent exact exchange with random phase approximation, quantum chemistry, quantum Monte Carlo, etc. But these are very slow. They're not going to be high throughput. So that's what so we can satisfy that edge with AFLOW-CCE, which is the correction scheme we're using. Oh, it's frozen. Okay, so CCE stands for coordination corrected enthalpies. What's the idea behind this correction scheme? You can have these ionic materials or ionic compounds, and they're going to have, we want to look at corrections that are based on their coordination. So here we have an example of calcium oxide. The atomic environment for each calcium each oxygen bond here is going to have 6 calcium sitting on around its environment, its local environment. So we have 6 calcium oxygen bonds. In titanium oxide, in the rutile phase, we're going to have 6 titanium oxide bonds. In this compound, we actually have a different number of calcium oxide bonds than we did in this system. So what we're going to have is we're going to have corrections that are dependent on the atomic environment. How many bonds do we have for each particular oxide to metal system? Okay. So how do we define these corrections? Well, we take the formation enthalpies from experiments. Okay, there's experiments, and we can find out what the formation enthalpies are. We can perform the calculations of the same phase using VASP. We take the difference between the experiment and what we calculate, and we define the correction based on the stoichiometry, the number of bonds, and this is the variable we're solving for. Okay, so we're going to extract a correction that is based on the species that's attached to the oxygen. In this case, we're looking at oxides. And that's also based on the coordination, okay, which defines, which is what, so that's how we define those corrections. So you can see here that we have a publication on this work. We have a table here based on, for the oxides, what metal is it attached to. And you can see here, for instance, for vanadium, we have different coordinations. Okay, so it's going to be based on the oxidation state. That's really the parameter we're varying here. Depending on the coordination, we're going to get different oxidation states. We can incorporate temperature effects. So we can actually calculate these corrections at room temperature, which is where experiments were performed. And then we can sort of extrapolate to zero Kelvin, okay, because our calculations are performed at 0 Kelvin. So we take the room temperature formation enthalpies, we fit them to the DFT formation energies, and we get our room temperature corrections. If we want to get the correction at 0 Kelvin, we need to calculate the thermal contributions. Okay, so that's going to be this vibrational data that we were doing in the last session, this thermomechanical calculations that Dr. Toa was showing you, we're going to subtract off these vibrational contributions. Remember, if you saw, you had FVIB. Okay, so that's that term that we want to subtract off, and then we can actually fit to the formation enthalpies of the system, and we can get the zero temperature corrections. Okay, so so for the binaries, we basically build the corrections based on the binaries, and then we're going to use those corrections for the ternaries. Okay, so based on what's bonded to oxygen and how it's bonded to oxygen, we can actually take the binary corrections and apply them to the ternaries. And you can see here that we compare it to an existing approach in the literature, which is called a quasi-FARE. FARE stands for fitted elemental reference energies, elemental phase reference energies. And you can see that CCE has a lower error with respect to the existing literature here for a wide variety of ternary oxides. We've actually generalized this, so it doesn't only just work for oxides. We can also look at halides. So these systems where they're bonded to fluorine, for instance, or chlorine. And you can see here that the errors from uncorrected to corrected are much lower. Okay, so this concept doesn't only apply for oxides, but it's going to apply more generally for all ionic materials. A very important idea here is that CCE doesn't only get better in terms of reducing the overall errors of the formation enthalpies, but it does so in such a way that it can actually correct for which is the lowest energy structure, right? The ground state. So here we have a few examples. We have 3 example systems where we know what the ground state is. And for instance, if we just run PBE, we're going to get a different reference phase. When we run CCE and we correct it, we correct the PBE calculation with the corrections, we will actually get the correct ground state system. So we show it for this aluminum 2 silicon oxide system here. We have it for cobalt oxide. So for experiment, we get rock salt. Even with scan, which is a much more expensive calculation, it's a meta GGA, we're actually going to get a different ground state. But when we correct these with CC, we'll actually retrieve back the right ground state that we expect from experiment. And the same for this manganese oxide system. All right, so you can run AFLOW-CCE to get a set of instructions for the CC module. You can feed it in a postcard, and it's going to give you the corrections. Okay, so first it needs to do an analysis of the oxidation numbers. So it's going to perform this analysis of the local atomic environment and figure out what is coordinated to what and how many bonds exist. And then it'll actually tell you what the oxidation state it is. It is what oxidation state it finds for the metals and then for the non-metal compounds. It'll give you the corrections both at room temperature and at 0 Kelvin for all of the different functionals here. And then there's even a way that CC has of guessing what the formation enthalpies are for that system. It's not necessarily going to be very accurate, but roughly speaking, using these corrections, we can actually guess what the formation enthalpies are. And so this is showing how we extract the experimental these experimental formation energies. You see that it's based on these corrections that we defined for all of the metals, plus oxygen or plus fluorine, plus chlorine, whatever. Okay, so with the command line, so you can run AFLOW-CCE equals postcard. So you feed in the postcard. You can get it for a specific functional if you feed in PBE, scan, LDA. And you can also feed in the DFT formation energies, and it'll actually give you the corrected formation energies based on what those DFT formation energies are. And in case the internal algorithm doesn't work, you can actually also feed in the oxidation numbers. And then if it has a correction based on those oxidation numbers, then it'll return back the values. So we have an online module. You can actually submit a postcard, and you can actually play with all the different parameters. You can select a particular functional. You can enter in the DFT formation energies. You can enter in the oxidation numbers. This is comma separated. You can hit submit and it'll run the calculation for you. And here we have a number of exercises. So I'm gonna stop sharing the slides, and we're gonna go into our breakout rooms. We have about 7 minutes to do these exercises. So it's actually pretty simple. But you're gonna start off by. Okay, so we're going to come out of the Jupyter notebook, and we're going to start we're going to start with an exercises in the Convex Home module, and you're going to go inside of 4 CCE, and you're just going to run some of these commands given these postcards. So it's pretty simple. It shouldn't take all that long. And I think we're going to be able to do that and go into our breakout rooms now. So let's go ahead and do that. I'm going to pause the recording. Okay, we're going to quickly go through the answers, just so that we're all on the same page. Let me share my screen. Okay, so first question asks, what is the oxidation number for this particular postcard that the CCE algorithm gives you? So we ran this one. So this, yep. So if you run the algorithm, if you run the command, you'll see that the oxidation numbers are, for oxygen, we get -2, which is exactly what we expect there. For molybdenum, we get +6. +6 is perfectly allowed for molybdenum, and +2 for lead. But the question is, why does one get +6 and the other one gets +2 and not vice versa? It's because molybdenum has a lower electronegativity than lead, and therefore a higher oxidation number. So that's some of the consideration that the algorithm's considering. That's some of the consideration that the algorithm puts into some of the, that's what the algorithm considers under the hood, let's say. Okay, so the next question is, what function has the largest CCE correction for this postcard? Okay, so we're going to run this command. If you guys didn't see, it's just CCE equals postcard equals the postcard of interest. So the largest CCE correction at room temperature. So here we have room temperature, room temperature, room temperature. The largest one, so this is plus 0.13. This is -205, and this is minus 0.13. So you see that the largest is for LDA for this particular structure. Okay, and then the last, let me just make sure there aren't any questions. And then for the last question, we want to know what are the formation enthalpies for the perovskite at zero Kelvin. And we have provided the DFT formation energy. So we use that additional parameter to input the numbers. And then we provide the order of the formation energies here, PB, LDA scan. We hit enter. And we'll see at 0 Kelvin, we get, what is the significance of positive and negative corrections? Well, it just depends on whether whether DFT incorrectly gives you a formation enthalpy that is larger than expected or smaller than expected. So it's not, I'm not sure that, well, I mean, we haven't done the analysis. I'm not sure, but I'm sure that for particular elements, depending on the electronegativity and all that, it's going to, some of them, it's going to be obvious that DFT is going to overcorrect or it's going to undercorrect.
We actually did this analysis when we looked at the paper. I don't think we found any consistent trend. I think a lot of it, like the actual values that you get, will depend a lot on which pseudopotential you're using.
Yep.
So this depends, like the actual value will depend more on the pseudopotential than anything else. So it tends to be kind of unpredictable, actually. We tried to look for general trends, but I don't think we found anything.
There you go. So yeah, for 0 Kelvin, you have the PBE value here. So -3449. For LDA, you get -3.412. And then for scan, you get -3.414. Okay, so that covers the session here. I don't see any additional questions, so I will close out the session for break. For we're gonna break for lunch now, and we will meet back at 2 p.m. Central Standard Time, and I will stop the recording. You guys are welcome to stick around. Let me stop sharing first, and then I'll